Good evening. Uh, we are supposed to do Unit 2 of Linear Algebra in this class, and there are some topics from Unit 1 that I want to cover in this lecture so that when we start the Unit 2, you do not feel any inconvenience. Okay, so first of all, I want to define linear transformation. What a linear transformation is: you have two vector spaces. These two vector spaces need not be same. You can take V and W, but the underlying field should be same. Underlying field should be same. And you say that you define a function t. So first of all, t is a function. So t from V to W first of all, and always remember TF and WF. What it remembers that V and W are both vector spaces with same base field, underlying field. So this, since it is a function, every element of capital A will, sorry, of capital V will have an image in W. So you take element X and element Y. So if this X is having image capital X and Y is having image capital Y, then what you say if you find X plus Y, then its image will be capital X plus capital Y. They say if you do alpha X, what is alpha? Alpha belong to the field. So the image will be alpha capital X. You combine these two things and it becomes alpha X plus beta Y will go to alpha X plus beta capital Y. So in functions language, we will say X is going to Tx and Y is going to Ty, implies alpha X plus beta Y will have image alpha Tx plus beta Ty. So first thing, then you can say T of alpha X plus beta Y will be equal to alpha Tx plus beta Ty. Now this is one thing. Now what happens is you have this capital V and capital W. You have this capital V and capital W. This capital V will surely be having 0 and this capital W will surely be having capital 0. So first theorem is T0 will be equal to 0, means image of 0 will always be 0. Now if T is linear transformation, then obviously it is linear transformation. If it is 1 1, if it is onto, if it is 1 1 and onto both. Okay, so you say that this is monomorphism, this is monomorphism, this is epimorphism, this is epimorphism, and this is isomorphism. We know this. Okay, now one more thing, special case. Always remember this special case. Special case is if V is equal to W, I mean P is from V to V, then we say this is linear operator. Then we say this is linear operator. And if W is equal to F, how we can take F? Because F over F is always vector space. So we take T from V to F, then we say this is a linear function. This is linear function. So I am not giving any example, I am just covering the theory part. Okay, so next thing is okay, we want T, this is very important, T from V to W. You see this is your V and this is your W. 0 will always be going to 0, but some other element, for example this element, is also going to 0, is also having image 0. This element is also having image 0. This element is also having image 0. It is condition on linear transformation that 0 will have to give image 0, but non-zero elements are also having the image 0. So what you do, you combine these elements, set of all those elements whose image is 0 in W, becomes, sorry, is called kernel T. Kurt means V belong to V such that TV is equal to 0. So we represent it by NT also, and is called null space of T. Null space of T. Most importantly, it becomes a vector space. It becomes a subspace. It becomes a subspace of, obviously, of left hand side means V, of capital V. Now one more thing, this is capital V and this is capital W. When this is a function, first of all, if it is a function, then every element of V will have image, but every element of W need not have pre-image. So there are some elements of W that are being covered by the elements of capital V. These are called range of T. So you represent it by RT, and this also becomes a subspace of capital W. Now, why we are doing this? Because we have a very important theorem which is called Sylvester law of rank nullity. Sylvester's law, or you say rank nullity theorem, which says eta T plus rho T will be equal to dimension of V. This thing will be equal to dimension of V. So this is the result. I will rub this. Next thing is T is monomorphism. We want to make T is monomorphism. Monomorphism mean one if and only if. Okay, if and only if NT means kernel T is equal to 0. So this is a very important result. This is the most important result. And second is T is epimorphism if and only if RT is equal to W. If and only if RT is equal to W. These two results are most important. We need these results in unit 2. Okay. Next thing is you have capital V, you have capital W, and when you have capital V and capital W, you find linear transformation. This is T. Then you find one more linear transformation T dash. Then you find one more linear transformation T double dash. You find one more linear transformation S. One linear transformation is zero linear transformation. It will always be there, but it says every element will have image 0. So you find collection of all possible linear transformations, from V to W, represented by whom V to W. Okay, and this is, in this you have 0 T, T dash, double dash, T1, T2, so and so, S, so and so and so. Many linear transformations are there, and you have a field, underlying field. This field will be the field which V and W have. So this thing, home VW over F is a vector space, and dimension of this is multiplication of dimension of V and dimension of W. And the corollary is you take this V, and instead of W you take V. Okay, you take V and V. So you will say home VV, or home V is also called LV. Okay, this will obviously be a linear, this will also be a vector space over the same field F. So LVF is a vector space, and obviously dimension will be square of dimension of V. So this is the result. We need this result. Now next thing is we have T is non-singular linear operator. So I am talking about T from V to V. So we are talking about non-singular linear operator is linear operator if and only if T is isomorphism. If and only if T is isomorphism. Isomorphism says 1 1 and onto both. But we have this result, we have the proof also. When we have T from V to V, dimension of V and V obviously is same, then it will become isomorphism even if it is only 1 1. If it is mono. If kernel T is 0. Okay, and one more thing is, we have not done this, but I am writing this. If and only if TB, which is called matrix representation of T, is a non-singular matrix. We can represent this thing by T determinant is non-zero. So this is a very, 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 very important result. We will use this in unit 2. Okay. One last topic is matrix representation of linear transformation. What we do is, we have capital V, we have capital W. When we have capital V, we have its basis E1, E2 up to En. Considering the fact that it is an n-dimensional vector space and it is an m-dimensional vector space. So this capital W also has basis, for example, F1, F2 up to so on, Fm. Now, this is your linear transformation. What we do is we find images of E1, E2, E3 up to so on, En. We find these images. Now these images, obviously these images belongs to W, and W has a basis. The basis is this. So what we do is, we represent, this is TE1 is element of W, and W1 has this basis. Element of vector space can be represented as linear combination of the basis elements. So this first element is written as alpha 11 F1, alpha 21 F2 up to so on alpha M1 Fm. In the same way, you have alpha 1 2 F1 alpha 2 2 F2 so F M2 Fm and up to so on alpha 1 n F1 up to so on Mn Fn. Now you say this is T, this basis is for example beta, and this basis is for example beta dash. You say this is T from beta to beta dash. Okay, sometimes it is represented by T beta beta dash, one and the same thing. Okay, one and the same thing, sorry. So in the same way, yes. So same representation. What you do is, you can do in two ways. Either you see, some people says that you find the coefficient matrix alpha 1, alpha 21 up to so on alpha m1, alpha 1 2, alpha 2 2 up to so on alpha m2, up to so on alpha 1n, alpha 2n up to so on alpha mn. Then they say take the transpose. Otherwise, you can directly say that this is the matrix and just write the element column wise, 2 1 up to so on m1, then 1 2 2 2 up to so on m2, up to so on 1n up to so on mn. So you can clearly visualize that this is a m cross n matrix. So this is the thing. Now one more thing which we will be using is, we will be having T from V to V. In all questions we will be having T from V to V. and we will be having a basis B, and this T single B, or you say T from B to B, or you say T from, sorry, you say T from B to B, one and the same thing, doesn't matter at all. And you can observe that this will be a n cross n matrix. This will be a n cross n matrix. So it is a square matrix. It is a square matrix. So we need these many things, and we start unit 2. So we'll start that. Thank you so much.